Okay, so now we're going to take the antiderivative and now apply it to something called differential equations and the indefinite integral. So it's just little stuff on notation, how we can write antiderivatives in different forms. So first of all, I'm going to actually define what a differential equation is. By the way, there's like a whole course in university that dedicates all the material to this type of thing. So a differential equation is an equation that contains the quotient of differentials, which are derivatives. So dy dx is equal to 4x. This is what we call a differential equation. And this looks familiar. You know, we've worked with this in the derivatives. Dy with respect to dx is a derivative. And so dx and dy actually do have names. They're called differentials. And when we take the quotient, we get the derivative of y with respect to x. So this isn't new. I'm just actually now calling it something different. I'm calling it a differential equation. So to solve a differential equation, so when you solve it, you actually have to find the antiderivative. So when we take the antiderivative of 4x, we actually get 4x squared over 2 plus c, which does simplify down to just 2x squared plus c. So to solve a differential equation, you're taking the antiderivative. Another symbol that represents the solution of a differential equation, also known as the antiderivative, is what we call the indefinite integral. So this y is equal to 2x squared plus c, that is the antiderivative. And a different way of actually stating it is the integral of 4x with respect to x. Okay, so 4x with respect to x, when we take the integral, so the integral is this funny little s symbol that I've just drawn here. The integral symbol just means you're going to take the antiderivative of 4x with respect to x to get 2x squared plus c. So just to name off the parts of an integral, 4x is what we call the integrand, which is the derivative of the function that we are searching for. Okay, so the function that we're searching for is the antiderivative, and when you take the derivative of that function, you get the integrand, which is 4x. And we can show that here. I mean, derivative of 2x squared just gives us 4x. So, and dx is the differential, which represents the variable that we're integrating with respect to. So we're integrating with respect to x in this situation. So here are some just common integrals that you can see on your formula sheet. I think this is in your note package where there's a couple mistakes here that I need to address. First of all, when we take the derivative of u, which is a power function, we add 1 to the exponent, okay, and then divide by that new exponent. But don't forget to add c, so I forgot that in the notes there. Anytime you take the derivative or antiderivative, of a constant, you get k times u plus c, okay? And here's some more antiderivatives. One that kind of sticks out, obviously, is e to the power of u. When you take the antiderivative, you actually just get the same thing, e to the power of u. 1 over u is a very specific type of function. When you take the antiderivative or integral, you get ln of u. So you'll notice that when I teach a lesson, I'll use the word antiderivative and integral very interchangeably because they're the same thing, okay? So here are some trig functions in here that you may see. Once again, they're all on your formula sheet, but they're all just the reverse of the derivative. Okay, so let's look at some questions in here. Okay, so evaluate each of the following indefinite integrals. Okay, so in other words, what is the antiderivative of x to the power of 5? So we'll start with this one. When we take the antiderivative or integral, we're just going to add 1 to the exponent. So we get 5 plus 1, which gives you 6. Divide by 6. And add the constant, and we're done. Okay, that's all we have to do. And so if we take a look at the next one, my integrand is negative 3x squared, and I'm integrating with respect to x. So once again, it's another power function. We're just going to raise 1 to the exponent, which is 3, and divide by 3. Add c for the constant, and therefore the 3 is actually reduced, so I get negative x cubed plus c. So that one's done. Now, 20 is a constant. Now, when we take the integral of a constant, we get 20, and you check to see what we're integrating with respect to. So we're integrating with respect to x, so we get 20 times x plus c. Once again, if you want to check your answers, just take the derivative of your integral, and you will get your original function back. So derivative of 20x gives me 20. Derivative of negative 3 negative x cubed gives me negative 3x squared, and that gives me my integrand. And then finally, derivative of 6x to the power of 6 over 6 gives me 6 times x to the power 5 over 6, which just reduces to x to the power 5. So it's really easy to just check, because you just take the derivative of your antiderivative, and then you'll get your original answer back. Couple things with the properties of integrals. If you're adding two separate functions within your integrand, you can actually split it up into two different integrals. You don't have to, though, but it's just something you could do. You could actually perform operations on it. So, for example, for this one here, I would expand the x in, for example, and I get 2x to the power of 4 plus 5x, and this is all with respect to dx. And by the way, I can split this up. You know, I can go integral of 2x to the power of 4 plus integral of 5x to the power of 1 with respect to dx. And I forgot I put dx right there. So you can split it up. You don't have to. You could just deal with each of these terms individually. It really doesn't matter which way you do it. When we do areas, sometimes you might want to split it up. But when we take the integral of 2x to the power of 4, I get 2x to the power of 5 over 5, okay? And then we're going to add the integral of 5x, which is just 5x squared to the power of 5x squared over 2. And then we're going to add the c value. So honestly, you can split it up, but you don't have to. So for this one, like, I won't split it up, because what I'm simply just going to get is, well, integral of 3x is just 3x squared over 3. And then the antiderivative, or integral of secant squared x, well, that's tan x. So when you take the derivative of tan x, you get secant squared x. So you can go in reverse just to double check that. And then add c, and we're done. Okay, so it's up to you. If you want to split it up, you can. You don't have to, though. It's, once again, sometimes it's easy just to do it all at once. So in the next podcast, I'm going to just do more complex examples. And so that's it.